we were in this quadrant 4 here. We're from 0 degrees to negative 90. Now when we're working with our inductance, now we're going to be up in our quadrant number 1 here, and we're going to be from 0 degrees to positive 90 degrees. So again, now when we're looking at this, we know that VR then, or VL is going to lead VR by 90 degrees. And VS is going to be somewhere in between there, depending on how, if we're more inductive or more resistive. If we're more resistive, we're going to be closer to 0 degrees. And if we're more inductive, we're going to be more closer to positive 90 degrees. My voltage source will shift more towards the inductor. Okay. Otherwise, it's all basically the same. Here's the resistance of a winding, and that's going to be treated as a whole separate resistor. Okay. And if you do the worksheets, we just did it as an ideal inductor, meaning that there was no internal resistance to that.
We didn't get that one.
No, I'm just holding it up. You already have the vector diagrams already. Yep, on your capacitance ones. I didn't print it out. Yep. If you want some worksheets, I got some of those numbers on it and all that. Huh?
You gonna save some trees?
Save some trees. And it really is. Everything is just the same. It just becomes more inductive. It's now from 0 to positive 90. The only difference is that we're going to have to be concerned with about the resistance of the winding of our inductor, but we're not going to deal with that until we get into chapter 13. They'll have you measure it and stuff in your lab and stuff like that, but we're not going to use it in our calculations until we get into chapter 13, where we're actually putting in a resistor, a capacitor, and an inductor. Then we'll incorporate the resistance of the winding. Okay? So again, just looking at our vector diagram, we know that, all these are going to be all at 0 degrees. So if I was doing my phase angle, my VR is going to start out at 0 degrees. My VL is just going to be leading by 90 degrees, and this is all in the book. So here's VR, that's our reference signal, that's at 0 degrees. Here's VL, that's at leading by 90 degrees. And then VS is going to be somewhere in between these two. But it'll always be leading or right on top of VR. And so if we're at, for example, let's say on this one here, if I was at my frequency cutoff, what would be my angle of my theta then? So if I'm at frequency cutoff on any RL circuit,
Positive 45 degrees?
Yeah, positive 45 degrees. So we'll just say that we're at my frequency cutoff, and that's my VF, and that's going to be at 45 degrees. It's going to be leading VR by 45 degrees. So again, very similar. The only difference is that phase angles just changed. Remember before, our voltage of our capacitor lagged VR by 90 degrees. The only difference is now that VL is going to be leading by 90 degrees. And then when we get into chapter 13, then we're going to combine the two, and then we're going to find out that we're going to have VL leading by 90 and VC lagging by 90, and VS can be somewhere in between VL and VC. It can swing 180 degrees. And then we'll talk more about the resistance of the winding and how that affects our circuit and stuff like that. And that affects our quality of our circuit. And when we're talking about band pass and notch filters and stuff like that, that's where that becomes important. All right. So the same thing, just like we did in chapter 10. The only difference is that we're going to have a positive angle. All right, so let's just do a little, so now we can do our little practice one here. The sheet that I did hand you out. All right, so this time we're going to kind of be a little bit more specific, kind of talking about, what is it that we're really actually doing when we're calculating out. So what we want to do is that we want to find fill in our blanks with the information that we have. And this time we're going to make sure we're calculating out our theta, because we're going to have you measure your theta using your oscilloscope in your labs. So if I want to, if I got a frequency at 500 hertz, what's going to be my first steps to figuring out how to calculate this thing out? Do I have X of C here?
Yeah.
Should be X of L.
Calculate your X of L.
Calculate out X of L. So what would be my first step that I want to do on my circuit here?
Calculate the X of L.
Yeah, calculate out my X of L. And how am I going to calculate out my X of L?
Resistance times your capacitor or your inductor.
Yep, 2 pi FL. So what do I get for at 500 hertz? What am I going to get at 500 hertz for X of L?
$314.2.
14.2. 314.2. Oh. Okay, so then we got, so now we got our X of L. Now what's our next step?
Find your R total.
Okay, now we can find our Z total, our impedance, which is a combination of resistance and reactance. So what, and how do I calculate out my, how do I calculate out Z? Two different methods that we can do.
Square root of r squared plus x of l squared.
Yeah, so we can do our square root of r squared plus x of l squared. So we can do it that way, and we can get our Z. But if we do the other method, we can go ahead and get our theta at the same time. And if we use our rectangular to polar function, then we can calculate out both our Z and our theta at the same time. So just looking at this with my inductor being at 314 ohms and my resistor at 10 kilo ohms, what would you expect my angle to be at? Very high or very low? Closer to 0 or closer to 90? Closer to 0, because my resistor is so much more bigger than the inductance reactance is. Okay, so then let's calculate out our Z, and so our Z is going to be closer to equaling R also. So we know that my Z is going to be pretty close to 10 kilo ohms. So even before we even enter in our calculator, you know, we can start taking a look at some of this stuff and checking our answers as we do it.
We got 1.07.
What'd you get?
1.07.
10K.
Is that 10?
I got 10K.
Yeah, you got 10K. It should have been real close. By the time you rounded it up, you should have gotten 10 kilo ohms. And then what do you get for an angle then?
1.8.
What was it?
1.8.
Yeah, so it should be a positive 1.18, did you say?
Yeah.
1.18. So yeah, so we're really close to the 0 there. Okay. So now what? Now what would be my next step? Yeah, we can find our current total. Or what I might do is, since I already have my angle and I know my voltage total, I go ahead and use my polar to rectangular function and get my voltage across VR and VL. So let's do that. Let's use our polar to rectangular function. Everyone remembers how to use their polar to rectangular functions? If not, I'm sure you do.
Oh. Oh, just go with 10. It's easier.
What do we get for VR and VL?
VR is 9.995.
What did you get?
I've got 9.995.
Did you use 3 volts?
No, never mind.
Alright, yeah.
Put it wrong.
You're on the right track, you're just using the wrong voltage. Alright, so what do we get for VR?
Oh, I'm in the wrong.
3 volts? By the time you round it up? Yeah, so by the time you round it up, it gets to be about 3 volts, but it'll be just slightly less than that. Because we know that my angle is at, we know that my angle is so close to, so here's VR, here's VL, and here's my VS, and so since VR, or my VS is at 3 volts, and we know that I got an angle of 0 degrees, I know then that my VS and my VR are going to equal at the very low frequency. So then what's left across VL then? Come up with a number. 0.0942 volts. Or 942 millivolts.
Yeah.
Or 94.2 millivolts. Yeah, very small.
How did you get that? Just put in that.
Yep, so you did the polar to rectangular function.
Yeah, the second function was 61.8. That's what I got. Yeah.
Okay, so you got what did you get?
You guys are using that 1.1.
One is 1.1.
1.8.
Do I have this wrong?
It should be 1.8.
Yes. 1.8.
Oh, okay.
So 1.8 is what we should have?
Yeah.
Yeah. All right, so if you use that, then I end up with something like that. Yeah, don't forget to correct this. You see something wrong up on here, make sure you correct it. Otherwise, everything else ends up going wrong.
Yep.
All right, now what's my IT going to be? You just figure out IT just taking our 3 volts divided by our 10 kilo ohms.
How did you get 94 then? Then it comes out to 41.8 million.
Did I write that one down wrong?
No, that's right.
It goes 3 comma 1.8.
Is it correct?
Yeah, that's right.
It's right?
Yeah, that's right.
It's right. Did you get it? What did you get, Isaac? I did 3, so do 3 volts, do second XY, then I'm going to put in my 1.8 degrees, I'm going to hit second, I'm going to go polar to rectangular. So yeah, I got
Now I got 94.
2.99, so this one really should be 2, we rounded this one correctly, I got 2.999. Let's get that one rounded correctly. 2.999 volts. Make sure what I have it as voltage peak. Peak to peak. Peak to peak. Make sure I get my units in there. And then if I do my second XY again, then I get 94.23 millivolts. Everyone agree with that?
Yep.
All right. So yeah, try that again. I think we'll.
Yeah, I got it.
Okay, you got it. Okay. Okay, then what's my IT? you got 300 microamps?
Yeah.
300 microamps. Peak to peak. Don't forget your units. All right. All right, so let's go ahead and fill in the rest of the chart on your own, and then we'll fill in the blanks here. If anyone needs help with any of this, on how to either use a rectangular polar function or a polar rectangular function, let me know. This would be a good time. Otherwise, double check your answer with the person next to you. We won't do it all up on the board one at a time. It'll take us forever. So just go ahead and whip through these, fill in the blanks, and then we'll analyze our data after we get that taken care of. What's that? No, not necessarily, right? Your degrees will change.
Current is probably going to stay the same.
A rectangular polar function, right? Okay, if you don't know how to do this, then find somebody that...
Current would stay the same. That's a series.
Yeah, we can just use Ohm's law. I mean, just take your voltage source divided by your impedance. Yeah, or you can take any one of your other components, the voltage divided by the resistance or reactance, whichever one. Since resistance means constant in a series circuit. On the midterm, that one really impressed me where people knew that one. What's that one? I'm surprised how many people got that. Oh, they where'd that one? Yeah, where it said in a series circuit, the generator current is frequently used as a reference, but in a parallel circuit, the generator voltage is almost always used as a reference. Explain why. Most people knew that one. But parallel circuits, voltage remain constant in both parallel circuit, and current remain constant in a
You've
series
only
circuit.
said it 1,000 times.
Huh?
You only said it 1,000
I know, but just the way that
times.
was worded, I didn't know if anyone would really catch
That was a little, I'm like, okay, wait a minute. I hope he's
Yeah.
not looking for something more complex than this.
Yeah, that's where, like on, we have PR, and then we have IC, IT and stuff, that's all our reference, that would be our current, and then on the parallel one, it's the opposite. Get them all along.
Oh, I didn't know I was supposed to be working through 'em.
Yeah, if you're struggling